The question says that a short bar magnet placed with its axis at 30 degree with a uniform external magnetic field of 0.25 Tesla experiences a torque of magnitude equal to 4.5 into 10 to the power minus 2 joule. What is the magnitude of magnetic moment of the magnet? Now in this question there is a bar magnet that has been placed in the magnetic field and it is making a 30 degree angle due to the influence of the torque that this magnetic field is putting on this bar magnet. Now we have to find out what is the magnetic moment of this magnet. Torque equals to mb sine theta. Now in this question we have been given the torque on magnet, that is we have been given this value tau, theta we have been given, and we have been given the magnitude of magnetic field, that is b. So we only need to find out m, where m stands for magnetic dipole moment of this bar magnet. Now putting all those values in the given equation, we will get the value of m as 0.36 ampere meter square. Thank you. The question says that a short bar magnet of magnetic moment m equals to 0.32 joule per Tesla is placed in a uniform magnetic field of 0.15 Tesla. If the bar magnet is free to rotate in the plane of the field, which orientation would correspond to its stable or unstable equilibrium? What is the potential energy of the magnet in each case? Now a bar magnet is placed in the uniform magnetic field like in the previous exercise we saw, and the magnetic moment is given over here, and the magnitude of magnetic field is also given, that is 0.15 Tesla. Now we have to find out if the bar is free to rotate, now which orientation would correspond to its stable equilibrium and unstable equilibrium. And the second question is saying that what is the potential energy of magnet in each case. Now we know that a bar magnet in uniform magnetic field experiences a torque given by tau equals to mb sine theta, where m is the magnetic moment and b is the magnitude of magnetic field, and theta is the angle between magnetic moment and the magnetic field. And potential energy of the system is defined as minus mb cos theta, where m and b means same and theta means same as well. Now equilibrium, whether it is unstable or stable equilibrium, occurs when torque on the system is 0 or torque on the bar magnet is 0. Now we see that in this torque expression there is a component of sine theta. Now when sine theta is equals to 0, then this torque is going to be equal to 0. So sine theta is 0 in two cases, either theta is equals to 0 or theta equals to pi or 180 degree. Now when theta is equals to 0, the magnetic moment is parallel to the magnetic field, and when theta is 180 degree, then magnetic moment is anti-parallel to the magnetic field. Now theta 0 is called stable equilibrium and theta equals to 180 degree is called unstable equilibrium, because if we try to change the angle when it is at 180 degree, even a slight change would make it unstable, whereas if we try to change the angle when theta is equals to 0 degree, then it will restore to its same point at theta equals to 0. Finding out the potential energy of the system in stable as well as unstable equilibrium, since we have known the expression that the magnetic field of the system is given, the potential energy of the system is given by minus mb cos theta. So we can find out u for stable would be theta equals to 0, giving the expression of 0.048 joule minus of 0.048 joule, and for unstable it is 0.048 joule. Thank you. The question says that a closely wound solenoid of 800 tons and area of cross section 2.5 into 10 to the power minus 4 meter square carries a current of 3 ampere. Explain the sense in which solenoid acts like a bar magnet. What is its associated magnetic field? Now let's first understand what a solenoid is. A solenoid is a coil of wire designed to create a magnetic field when an electric current passes through it. The magnetic field inside the solenoid is uniform and resembles the field of a bar magnet. The resemblance occurs due to the alignment of magnetic field lines creating clear north and south pole. Now how does the solenoid mimic a bar magnet? When the current flows through the solenoid, it generates a magnetic dipole moment, and the solenoid behaves like a bar magnet with a distinct magnetic moment pointing from south to north pole along its axis, that is inside. Now magnetic moment is defined as m that is equals to n times I times A, where n is the number of turns of the wire of the coil and I is the current flowing through it, and A is the area of cross section of solenoid. That is area of cross section of solenoid is this. Now we have assumed here that this coil winding is so tight that we can assume that each and every coil is a circle. So magnetic moment is defined as n times I times A. Now here the data has been given for the number of turns, the current in the solenoid, and the area of cross section. After substituting in this formula, we will get a value of 0.6 ampere meter square, which is the magnetic moment of this solenoid when the current is flowing through it. Thank you. The question is saying that if a solenoid in exercise 5.5, it is talking about the previous exercise, is free to turn about the vertical direction and the uniform horizontal magnetic field of 0.25 Tesla is applied, what is the magnitude of torque on the solenoid when its axis makes an angle of 30 degree with the direction of applied field? Now previously we saw that there was a solenoid of 800 turns in which the current was flowing in the solenoid, and it has a cross section area that was given. Now it was not subjected to any external magnetic field. Now in this question, that solenoid is subjected to external magnetic field of magnitude 0.25 Tesla. So we can assume the problem to be like this. Magnetic field is from left to right direction of 0.25 Tesla magnitude, and the solenoid is making 30 degrees. The axis of solenoid is making 30 degree with this magnetic field. Now we have to find out torque on the solenoid. Now we know that torque on a magnetic dipole in the magnetic field is given by tau equals to mb sine theta, where m is the magnetic dipole moment. Now here solenoid will act as a magnetic dipole with the given magnetic dipole moment, and b is the magnitude of magnetic field, that is 0.25 Tesla, and sine theta, where theta is the angle between the solenoid axis or the magnetic dipole and the magnetic field, external magnetic field. Now based on the previous data, we have the magnitude of magnetic dipole moment, that is 0.6, and we have been given the magnitude of magnetic field, external magnetic field, that is 0.25 Tesla and sine 30 degree. If we substitute these values in this formula, we will get the value of torque as 0.075 the Newton meter. Thank you. The question says that a bar magnet of magnetic moment 1.5 joule per Tesla lies aligned with the direction of a uniform magnetic field of 0.22 Tesla. What is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment normal to the field direction and opposite to the field direction? And what is the torque on magnet in case 1 and 2? So here the question is saying that we have got a magnet which is under uniform magnetic field. So if we assume this to be the uniform magnetic field and this to be the magnetic axis, now we have to find amount of work required by an external torque to turn the magnet so as to align its magnetic moment normal to the field direction. So initially it was aligned in the magnetic field. Now we have to turn this magnet so as to align it perpendicular to the magnetic field. In the first case, normal to the field direction, and in the second case we have to align it opposite, that is from this state to this state. So upon turning the magnet normal and opposite, we have to find out what is the work done by external torque that is required. And the second question, we have to find out what is the torque on the magnet in case of 1 and 2. Now in second case, we have to determine if we have turned this magnet, then what would be the torque acting on this magnet. In the first case, like this, in 90 degree, and in the second case, that is theta equals to 180 degree, where theta is the angle between the axis of the magnet and the uniform magnetic field. Now we know that torque on a magnet is given by tau equals to mb sine theta, where m is the magnetic moment, b is the magnitude of the magnetic field, and sine theta, where theta is the angle between the magnetic moment of the magnet and the magnetic field. We also know that work done by external torque is equals to final potential energy minus initial potential energy. and the magnetic potential energy is defined as U equals to minus mv cos theta, where m is the magnetic moment, b is the magnitude of magnetic field, and theta is again the angle between m and b. So let's proceed to solving. So work required by the external torque in aligning the magnet normal to the field, that is from theta equals to 0 degree to theta equals to 90 degree. We will find the initial and final potential energies. Initial potential energy will correspond to the theta equals to 0 degree, and final potential energy will correspond when theta equals to 90 degree. So using the formula above, we have calculated U initial, that is equals to minus 0.33 joule, and U final would be equal to 0 joule, because cos 90 would be equal to 0. Now work done would be equal to U final minus U initial, and that would give us 0.33 joule. Now similarly, we will proceed to the second question that said that from theta equals to 0 degree to theta equals to 180 degree. So using the same approach, we will find the U initial, that is when theta equals to 0 degree, it would be equal to minus 0.33 joule, and U final would be equal to 0.33 joule. So the work done would be 0.33 joule minus of 0.33 joule, that would give us 0.66 joule. Now the second part question said that what is the torque on the magnet when theta is equals to 90 degree and when theta equals to 180 degree. So we saw earlier that torque is defined as mb sin theta, or the cross product of magnetic moment and the magnetic field. Here m is the magnitude of magnetic moment and b is the magnitude of magnetic field, and sin theta, where theta is the angle between m and b. So when theta equals to 90 degree, we will get torque of 0.33 Newton meter, and when theta equals to 180 degree, we will get a torque of 0 Newton meter. Or visualizing this, when the magnet is in this state, we will get a torque of 0.33 Newton meter, and when the magnet is in this state, that is opposite to the magnetic field, we will get a torque of 0 Newton meter. We also know that this position is the unstable equilibrium position. Thank you. The question says that a closely wound solenoid of 2000 turns, an area of cross section 1.6 into 10 to the power minus 4 meters square, carrying a current of 4 ampere, is suspended through its center, allowing it to turn in a horizontal plane. Now we have to find out what is the magnetic moment associated with the solenoid, and what is the force and torque on the solenoid if the uniform horizontal magnetic field of 7.5 into 10 to the power minus 2 Tesla is set up at an angle of 30 degree with the axis of solenoid. So there is a solenoid and that is hanging. So we can assume from the top view that the solenoid is this is the solenoid, and a uniform magnetic field of magnitude this much, that is 7.5 into 10 to the power minus 2 Tesla, is set up at an angle of 30 degree. The angle between this solenoid axis and the magnetic field is 30 degree, and we have to find out what is the magnetic moment associated with the solenoid. So magnetic moment will not be influenced by the magnetic field. So magnetic moment is defined as m equals to NIA, where n is the number of turn of the solenoid and I is the current flowing through it, and A is the area of cross section of the solenoid. We have been given the data, all three data, so we can find out the magnetic moment. And the second question says that what is the force and torque on the solenoid when this magnetic field is set up. So torque on the magnetic dipole is given by mb sin theta, that is m is the magnitude of magnetic moment and b is the magnitude of magnetic field, and theta is the angle between the magnetic moment and the magnetic field, and here it is theta equals to 30 degree. We also need to tell what is the force on the solenoid. So we know that since the magnetic field is uniform, no net force would be acting on this solenoid by the uniform magnetic field, so force is going to be 0. Now let us calculate the magnetic moment and torque on the solenoid. So magnetic moment would be equal to NIA, where n equals to 2000 and I is 4 ampere, and area of cross section is 1.6 into 10 to the power minus 4 meter square. So we will get a value of 1.28 ampere meter square. And the second question said that what is the torque on the solenoid. Since we know that the magnetic field is uniform, so force is going to be 0. So calculating torque, we can use the formula mb sin theta, where m is 1.28 and the magnetic field is 7.5 into 10 to the power minus 2, that is given. So we will get a value of 4.8 into 10 to the power minus 2 Newton meter torque. Thank you. The question says that a short bar magnet has a magnitude of magnetic moment of 0.48 joule per Tesla. Give the direction and magnitude of the magnetic field produced by the magnet at a distance of 10 cm from the center of the magnet on the axis and as well as the equatorial lines of the magnet. So if we assume that this is our magnet, bar magnet, and we have to find out the magnetic field at a point which is on the axis and on the equatorial point, equatorial line, that is the perpendicular bisector of the magnet. Now for a fact we know that a short bar magnet behaves as a magnetic dipole with a magnetic moment m. Now magnetic field at a point on axis or the bisector or the perpendicular bisector is given by the formula B on axis is mu naught by 4 pi multiplied by 2 into magnetic moment of the magnet divided by r cube, and on the equatorial position it is given by mu naught m by 4 pi r cube, where r is the distance from the center of the magnet to that point and m is the magnetic moment of the bar magnet. Now using this formula we can easily find out what is the magnetic field on the magnitude of magnetic field on the axis and on the equatorial point. So substituting the formula we will get the magnetic moment on the axis as 9.6 into 10 to the power minus 5 Tesla, which will be along the magnetic moment, and on the equatorial position it will be 4.8 into 10 to the power minus 5 Tesla, which will be directed opposite to that of the magnetic moment of the magnet. Thank you. The question says that a short bar magnet placed in the horizontal plane has its axis aligned along the magnetic north-south direction. Null points are found on the axis of the magnet at 14 cm away from the center of the magnet. The Earth's magnetic field at the place is 0.36 Gauss and the angle of dip is 0. What is the total magnetic field on the normal bisector of the magnet at the same distance as the null point? That is from 14 cm from the center of the magnet. The question is hinting that it has given the magnetic field at the axis and we have to find out the magnetic field at the perpendicular bisector of the bar magnet. At 14 cm away from the center of the axis there is a null point. And what is null point? Null point is the field due to magnet is equal and opposite to the horizontal component of the Earth's magnetic field. Since the dip angle is 0, at null point the net magnetic field is going to be 0. That is, the magnitude of magnetic field due to the bar magnet would be equal to the magnitude of magnetic field of the Earth's magnetic field, and its direction will be opposite. That's why it will cancel out each other. So in that way we have been hinted the magnitude of magnetic field at the axis of the bar magnet at 14 cm. And also we know that B at axis, magnitude of magnetic field at the axial position is given by mu naught 2m by 4 pi r cube, where m is the magnitude of magnetic moment, and at the equatorial position it is given by mu naught m by 4 pi r cube, and B at axis is equals to 2 into B at equatorial position. That is, B at axis is 2 times that of the B at equatorial point, where r is same. That is, if we find out the magnitude of magnetic field at the 10 cm away from the center of the magnet on the axial position, then let's assume that its magnitude is A. Then the magnitude of magnetic field at the equatorial position at the 10 cm away from the center would be equal to A by 2. So let's proceed. If at 14 cm from the center of the magnet there is a null point, then B at axis at 14 cm must be equal to B at Earth, as we said, and that will be equal to 0.36 into 10 to the power minus 4 Tesla in opposite direction from that of the Earth's magnetic field. So we will get this expression, that is mu naught 2m by 4 pi r cube would be equal to 0.36 into 10 to the power minus 4 Tesla. Now total magnetic field at the normal bisector or the equatorial position at 14 cm is given by the magnetic field due to the Earth plus the magnetic field due to the bar magnet. At the equatorial position, the direction of magnetic field by the bar magnet will be equal to the direction of magnetic field by the Earth, so they both will add up. Now the total magnetic field would be contributed by that of the Earth and the magnetic field by the magnet. since we know that B by earth would be equal to 0.36 Gauss, and B at magnet would be equal to half of that of the B at axis, and B at axis is 0.36 Gauss, so it would be equal to 0.18 Gauss. So the total magnetic field would be 0.54 Gauss. Thank you. The question says that if the bar magnet in exercise 5.13 is turned by 180 degree, where will the new points be located? So basically it is referring to the previous exercise, that is 5.8. So in that question there was this bar magnet which was in the horizontal position with the magnetic field, and the null point was on the axis. And if we assume that this was the direction of magnetic field due to the bar magnet, that is Bm, we have shown it by that Bm. So the Earth's magnetic field was in the opposite direction, so on the axis there was the null point. So now the magnet has been reversed to 180 degree. So now its magnetic field on the axis has a direction opposite to that of the initial direction. That is, now it is from right to left, which can be seen over here. Now we have to find out new null point. So we know that at null point the net magnetic field is 0, that is magnetic field due to the magnet will cancel out the magnetic field due to the earth. So we have to find out at what point the magnetic field will be 0, the total magnetic field will be 0, or the null point of the magnet. So it will be on the equatorial position now, because along the axis the magnetic field gets aligned, the direction of magnetic field is same to that of the Earth's magnetic field, so we can't find it on the axial position, so it will be on the equatorial position. Now B at equatorial position is given by mu naught m by 4 pi r cube, where r is the distance from the center of the magnet. Now here we have to find out at what point r1 will the magnetic field due to the magnet will be equal to 0.36 into 10 to the power minus 4 Tesla, or the Earth's magnetic field, or the magnitude of Earth's magnetic field. So we have to find out r1 over here. Now we know from the previous question that mu naught into 2m by 4 pi r cube was equal to 0.36 into 10 to the power minus 4 Tesla, where r was 14 centimeter. So this is the magnetic field on the axis of the magnet, which was the case in the previous question. At r equals to 14 there was a null point, so it equals the magnitude of magnetic field to the earth. So we know this. Now we have to find out r1 for the same magnitude of magnetic field. So when we divide this both equations, we will get 0.14 meter or 14 centimeter by r1 cube, that is, this is the unknown, would be equal to 2. So from this equation we can find out r1, which will be equal to 11.1 centimeter. That is, the new null point will be at the equatorial position at 11.1 centimeter away from the center of the magnet. Thank you. The question says that predict the direction of induced current in the situation described by the following figure 6.15 from A to F. Now there are 6 figures. In all these figures we have to find out what is the direction of induced current in the coil upon either a moving magnet or there is change in current in the nearby circuit. So we will use Lenz's law to find out the direction of current, and Lenz's law says that the direction of induced EMF will oppose the change in flux that created it. For example, we can see the demonstration over here. Like if the north pole of the bar magnet is coming close to a coil which is stationary, now we see that the flux is increasing, so the current will be induced in this coil such that north pole will be created over here, so that it will oppose the moving magnet towards it. So the current will flow in the direction that would create stronger north pole over here. Now similarly, when the magnet will move away from this coil, then south pole will be there because it will oppose the motion, then it will create a south pole over here so that it attracts the moving magnet and it opposes the movement of the magnet. So let's use this to find out what is the direction of current in each of these diagrams. So in the first diagram we see that the south pole of the magnet is approaching over the Q side of the circuit, So we can see from this figure that since south pole is coming near, so this current, induced current, will be such that south pole will be created over here momentarily, so that the direction, the movement of bar magnet will be opposed. So in order to create south pole over here, north pole must be created over here. So if we apply the right hand thumb rule, we can see that in order to create north pole in the left side, the current must flow through in this direction, anti-clockwise direction, that is QRP. So the direction of current is going to be QRP and Q again. Similarly, in this figure, we see that south pole is moving towards the Q point. So again, the induced current will be produced such that south pole gets created over here, north pole gets created over here. So we can say that from the right hand thumb rule, the current will flow from PRQ in this circuit, and since north pole is moving away from this coil as in this diagram, so south pole will be created over here. So in order to create the south pole over here, north pole must be created over here, and applying the right hand thumb rule, we can say that the current will be in anti-clockwise direction in this circuit, which means that the current will flow from Y, Z and X. Let's move to the next figure. In this figure, we have tapping key just closed. Now here tapping, if the tapping key just got closed, it means the current started flowing, and when current start flowing, we see that the flowing current will create north pole over here and south pole over here. So the induced current in this circuit will be such that north pole gets created over here and south pole gets created over here. And by applying right hand thumb rule, we can say that again, in order to create north pole over here, the current should be in this direction, so it should be Y, Z, X. Now in this question, we see that rheostat settings being changed. So the pointer is decreasing the resistance, it means the current would be increasing in here, and this axis, Y, Z segment of this coil is much away from us than YX section of this coil. So if the current is increasing over here, north pole will be created over here and south pole will be created over here, and again we can say that north pole should be created in this coil over here and south pole should be created over here. Now since it is much nearer to us, so in order to create the north pole, the current must flow through YXZ, or we can say that the current will flow from, the direction of current will be from YXZ and again Y. Now in this diagram, we see that tapping key just released, or we can say that the current has just stopped. Now earlier when the current was flowing, we can see that this wire is hidden from the solenoid. It means that the circular turn is like this. Now earlier when the current was flowing, it would be such that the north pole should be here by right hand thumb rule, and south pole would be here. Now just after releasing this tap key, north pole has decreased, or we can say that the north pole of the magnet has been released. So south pole will be created over here and north pole will be created over here, and for creating south pole over here, we can say that the direction of the current must be in this opposite direction, or X, R, Y direction. And in this sixth figure F, we see that current is decreasing at the steady state. Now here in this line, the magnetic field direction would be such that the magnetic field will be 90 degree to the area vector of this coil. So we can see in this diagram that if that is the case, phi is going to be 0, as phi is the dot product of magnetic field and the area vector. So there would be no current that is produced in this circuit, in this coil. Thank you. The question says that use Lenz's law to determine the direction of induced current in situations described in figure 6.16. A wire of irregular shape turning into a circular shape. This figure describes a wire that is of irregular shape and it is turning back into a circular shape. And the second question is a circular loop being deformed into a narrow straight wire. So earlier it was a circular loop, now it has been transformed into a straight wire. So we have to find out what would be the direction of induced current in both the cases. In the first case, the magnetic field lines are going into the plane, and in the second case, it is coming out of the plane. Now we will be using Faraday's law and Lenz's law in order to understand and find out what would be the direction of current in this cases. The Faraday's law says that the EMF, induced EMF, due to which the current would flow, would be equal to minus of d phi by dt, where d phi is the change in flux and where flux is the dot product of magnetic field and the area vector. And Lenz's law says that the direction of induced current will oppose the change in flux that created it. So we will have to focus on the flux and how it is changing, and the flux will be opposed, the change in flux will be opposed. That's how the current will be produced. So in the first case, we see that irregular shaped wire, when it turns out to be a circular shape, then the area will increase, or as flux was defined as B dot A. So since area will increase, d phi or phi will increase. So the induced current will oppose the increase in phi or the flux, or opposite magnetic field will be created. So initially the magnetic field was going into the plane, so magnetic field out of the plane will be created, and thus in order to create magnetic field out of the plane, that is coming out of the plane, the current has to flow in anti-clockwise direction, that is A, D, C and B. So by applying right hand thumb rule, we can say that if the current flows in anti-clockwise direction, then the magnetic field will be coming outward, and that's how the current will be induced. The current will be induced. In the second case, it says that the area is decreased or flux is decreasing, d phi is decreasing. So the induced current will support the flux to restrict it from decreasing, and thus the magnetic field will be in the same direction as before, or the magnetic field will continue to be out of the plane, and thus we will say that in order to have magnetic field out of the plane, just like before, the anti-clockwise direction current should flow, or A dash, D dash, C dash, B dash should be the direction of current. Thank you. The question says that a long solenoid with 15 turns per centimeter has a small loop of area 2 centimeter square placed inside the solenoid normal to its axis. If the current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 seconds, what is the induced EMF in the loop while the current is changing? So here there is a small loop of wire of area 2 centimeter square is placed inside a solenoid. So just imagine that if solenoid is seen from its left or right along the axis as this, then there is a small loop of wire of 2 centimeter square placed inside the solenoid. Now we have to find out what is the induced EMF in this small wire, subjected that the current in this solenoid is changing from 2 ampere to 4 ampere in 0.1 second. Now if the current is changing, then obviously the magnetic field is going to be changing. Now if magnetic field is going to be changing, then there is a flux that is changing inside this loop as well, and flux is changing with time, so there will be induced EMF. Now Faraday's laws of electromagnetic induction says that the induced EMF E in the closed loop is proportional to the rate of change of magnetic flux phi b through the loop, and that is given by induced EMF is equals to minus d phi by dt. Now magnetic field inside the solenoid is given by B equals to mu naught Ni, where mu naught is the permeability of the free space, N is the number of turns per unit length of the solenoid, and I is the current. Now magnetic flux is defined as phi b equals to b dot a, that is the dot product of magnetic field and the area vector. Now for loop normal to the solenoid, as in the case of our question, theta is equals to 0, so the dot product will result out to be ba, as cos theta is equals to 1. Now let's calculate the induced EMF. So as we knew that induced EMF is given by minus d phi by dt, so we have to calculate the change in flux and we have to divide it by time, duration of time. So change in flux, we can see that, and since current is changing from 2 ampere to 4 ampere, so this value determines the delta t, and this is the number of turns per unit length in the solenoid, and this is the mu naught. So this results out to be the magnetic field of the solenoid, 4 pi 10 to the power minus 7 multiplied by 1500 into 2.0. So here 1500 comes from this data that has been given in the question, 15 turns per centimeter. Now if we divide, it has been given that 15 turns per centimeter. Now if we turn this centimeter to meter, then we will get 15 meter equals to 100 centimeters. So we will have to multiply it with 100, so we will get 1500 turns. So that's how we got 1500 multiplied by the area of the coil, that is 2 into 10 to the power minus 4 Weber, divided by time, duration of time, that is 0.1 seconds. So here we will get 7.54 microvolt. Thank you. The question says that a rectangular wire loop of side 8 cm and 2 cm with a small cut is moving out of the region of uniform magnetic field of magnitude 0.3 Tesla, directed normal to the loop. What is the EMF developed across the cut if the velocity of the loop is 1 cm per second in the direction normal to the longer side and shorter side of the loop? For how long does the induced voltage last in each case? So here magnetic field is normal to a rectangular loop. I have shown it with a magnetic field going into the plane, and the rectangular loop is lying on the plane of the paper of side 8 cm and 2 cm. The loop is placed normally to the magnetic field. Now when this loop is taken out of the magnetic field in either way, like in this way, parallel to the 2 cm side and parallel to the 8 cm side, so we have to calculate what is the induced EMF in both the cases, and also we have to find out what would be for how long does the induced voltage last. So we know that the EMF induced in a moving conductor in the magnetic field is given by this formula, E equals to minus d phi by dt. If the loop moves out of the magnetic field, then it is given that this expression turns out to be B times L times V, where B is the magnitude of magnetic field and L is the side of the parallel to motion and V is the velocity of the loop. Now there are two cases. At first, the movement is parallel to the 2 cm, or longer side is normal to the motion, that is movement is along 2 cm. So in this case, the velocity, we have been given the velocity, we have been given the B, and we have also been given the L, that is length of the side parallel to the motion. In this case, L is going to be 0.08 meter and magnitude of magnetic field is 0.3 Tesla and velocity is always 0.01 meter per second. So we will get the answer to be 2.4 into 10 to the power minus 4 volt in this case. Now the question also asked duration of the induced voltage. Now for the time the flux will change, there will be induced voltage. Now for how long will the flux change? Starting from the movement of the coil till the coil has moved 100% out of the magnetic field, there will be the induced voltage. Now since this side is moving out of the magnetic field, so we can get the time with by dividing the velocity from 2 cm. So 2 cm by 1 cm per second, we will get 2 seconds. Similarly, for shorter side normal to motion is given by BLV, where L is the length of side parallel to the motion. Now in this case it is going to be 0.02 meter. Rest of the things will remain same. And similarly in this case also, since the motion will be in this direction, now this side will go out of the magnetic field. Now how long will it take? 8 centimeter by the speed, that is 0.01 meter per second. So we will get time duration of 8 seconds. So 6.6 into 10 to the power minus 5 volt will remain for 8 seconds. Thank you. The question is saying that a 1 meter long metallic rod is rotated about an angular frequency of 400 radians per second about an axis normal to the rod passing through its one end. The other end of the rod is in contact with the circular metallic ring. A constant and uniform magnetic field of 0.5 Tesla parallel to the axis exists everywhere. We have to calculate the EMF developed between the center and the ring. Now there is a rod which is rotating about one of its end, and there is another end which is in contact with the axis, which is in contact with the ring, which has not been drawn in the picture. So we have to calculate the EMF generated between this point and this point 1 and 2. Now under given conditions, and the condition is there is a magnetic field that is parallel to the axis of rotation of the rod of magnitude 0.5 Tesla. So the magnitude of this magnetic field is 0.5 Tesla, and the omega is 400 radians per second. That has been given in the question. So we know by Faraday's laws of magnetic induction that EMF is induced when the conductor moves in the magnetic field, and induced EMF depends on the relative motion of the conductor and the magnetic field. And the formula for electromagnetic induction as per the Faraday's law is given by E, or the EMF, is equals to minus of d phi by dt, where phi is the flux, magnetic flux, defined as B dot A, where B is the magnetic field and A is the area vector. And now in this present case, the rod sweeps out an area as it rotates, changing the magnetic flux through it. Now, for the sake of this question, we will consider a rod of length L. We haven't given the measurement of this length, that is 1 meter. So let us assume that this is the length of the rod L, and there is a small element of length dx at a distance that is x from the axis of rotation. Now the motional EMF that is generated in this section is given by E is equals to B VL. We know that this is the formula for motional EMF. Now for this section, for the section of length dx, it would be equal to V times dx times B. Now V at the distance x in a circular rotation is given by V is equals to omega times x. So we can write it as B times omega x times L that is x. Now we will have to integrate this expression from 0 to L for the entire length of the rod. So total EMF would be equal to integration of B omega x dx from 0 to L, where B is the magnetic field, omega x is the V part of this formula, and dx is the length of the small section of the rod. Now after this integration, we will find out that EMF is equals to B omega L square by 2, and after substituting the values, we will get the value of 100 volts. So this is the EMF developed between the center and the ring. The question says that a horizontal straight wire 10 cm long extending from east to west is falling with a speed of 5 meter per second at right angles to the horizontal component of the Earth's magnetic field, that is 0.30 Weber per meter square. What is the instantaneous value of EMF induced in the wire? What is the direction of EMF, and which end of the wire is at the higher electrical potential? So in this question, it has been given that a wire of 10 meter in length, this wire, let us assume that this is 10 meter in length, it is falling down with a speed of 5 meter per second, and it is subjected to a uniform magnetic field of magnitude 0.30 into 10 to the power minus 4 Weber per meter square. Now we have to find out what is the induced value of EMF in this wire. So we know that when a conductor moves in a magnetic field, and EMF is induced due to the relative motion between the conductor and the magnetic field. Now Faraday's laws of electromagnetic induction says that the induced EMF is equals to minus of d phi by dt. In this case, the motional EMF would be equal to BVL, where the direction of magnetic field and velocity of the wire is perpendicular to each other, and this is the length of the wire. So let's calculate the instantaneous value of induced EMF. So using the formula above, we know that E is equals to BVL. Sine theta here comes from the cross product of V and B, that is V cross B. So here we know that theta is 90 degree because the wire is falling down, and we have to calculate the EMF due to the magnetic field and due to the horizontal component of the magnetic field, Earth's magnetic field. So the theta will be equal to 90 degree here. Now L is going to be 10 meter because this is the length of the wire that has been given, and V is the velocity at which it is falling, and B is the magnitude of magnetic field. Now substituting in this formula, we will get a value of 1.5 into 10 to the power minus 3 volts. Now for the direction of EMF, using the right hand thumb rule as well. So this is a vector of V, this is vector B, and this is 90 degree between them. Now if the right hand thumb rule says that the cross product of the two vectors is, the direction of cross product of two vector is along the thumb. So when V cross B is there, then the direction will come from west to east. That's how we know that the EMF is directed from west to east. Now the third question was higher potential end of the wire. The direction of the induced EMF determines the higher potential end. Since the EMF is directed from west to east, the eastern point of the wire is going to be at the higher potential. So this point, eastern point, is going to be at the higher potential. Thank you. The question says that current in a circuit falls from 5 ampere to 0 ampere in 0.1 seconds. If the average EMF of 200 volt is induced, give an estimate of the self-inductance of the circuit. Now we know that self-inductance is a property of the circuit where the change in circuit induces an EMF in the same circuit. Now Faraday's laws of electromagnetic induction says that induced EMF would be equal to E equal to minus of L delta I by delta T, where delta I is the change in current and delta T is the duration in which this change in current has occurred, and E is the induced EMF and L is the inductance of the circuit. Now we have to find out, give the estimate of self-inductance, that is we have to find out the value of L in Henry, which is the self-inductance. So we have been given the data of initial current, that is 5 ampere, final current, that is 0 ampere, since the current dropped from 5 ampere to 0 ampere in 0.1 second. So delta T, duration of time, would be equal to 0.1 second. Now average EMF is given, that is 200 volts. So after substituting these values in this formula, we will get a value of L, that is equals to 4 Henry. Thank you. The question says that a pair of adjacent coils has a mutual inductance of 1.5 Henry. If the current in one coil changes from 0 to 20 ampere in 0.5 seconds, what is the change of flux linkage with the other coil? Now mutual inductance, we know that it is a property of pair of coils that quantifies the ability of one coil to induce an EMF in the another coil due to the changing in current. So as there is a change in current in this coil, then the associated magnetic flux will change, and that changing magnetic flux will induce EMF, because we know that by Faraday's law, EMF is given by minus of d phi by dt. Since this change in flux will interact with the second coil, and this change will happen with time, so an associated EMF will induce in another coil. Now in this question we have to find out what is the change of flux linkage. So we have to find out the change in flux. Now flux is given by mutual inductance times the current. Now change in flux can be given by mutual inductance multiplied with the change in current. Now here we have been given the mutual inductance, that is 1.5 Henry, and we have also been given the change in current, that is 0 to 20 ampere. So final current is 20 ampere and the initial current is 0 ampere. So we can easily find out using this formula the change in flux linkage, that would be equal to 1.5 times 20, and that will be equal to 30 Weber. Thank you. The question says that a 100 ohm resistor is connected to a 200 volt 50 Hz AC supply. What is the RMS value of the current in the circuit, and what is the net power consumed over full cycle? Now if we try to represent it in a circuit diagram, then it is like this. This is the AC supply of 50 Hz and 220 volt. Now unless it's specified, this voltage is in the RMS form, and there is a resistor of 100 ohm which is connected to the circuit in a series circuit. To express the AC power in the same form as DC power, RMS value is used, and RMS is defined as the square root of the average of a squared quantity. IT, if we define current varying with time as Im sin omega t, where Im is the peak current and sin omega t is the sinusoidally varying quantity. Now I RMS square would be equal to 1 by t of integration from 0 to time period, where t is the time period, Im squared sin squared omega t dt. Now if we find out this integration, definite integration, then we will come to know that IRMS squared would be equal to Im squared by 2, or we can say that IRMS is equals to peak current by root 2. Now in this question we have been given the VRMS, that is 220 volt, and the resistance, that is 100 ohm, and the frequency. So we have to find out IRMS. Now IRMS can be given as VRMS by R. So VRMS is 220 volt and 100 ohm is the resistance, so it is equals to 2.2 ampere. Now net power can be given by the formula IRMS squared times R, where we know that IRMS is equals to 2.2 ampere. So upon substitution we will get a value of 484 watts. Thank you. The question is saying that the peak voltage of an AC supply is 300 volt. What is the RMS voltage? And the RMS value of the current in the circuit is 10 ampere. What is the peak current? So we saw this derivation in the earlier question of the RMS value of current. Now RMS value in AC current is used to make it equivalent to the DC current, so that the formula for current and power can be used. So we have to find out here peak voltage of an AC supply at 300 volt. So from this derivation we came to know in the previous question that IRMS is equals to Im, or the peak current, divided by root 2. So here we have to find out what is the, now this goes same with the voltage, that is VRMS would be equal to V peak divided by under root 2. Now the question asked what is the RMS value of voltage, that is VRMS. We have to find out VRMS, and we have been given the peak voltage of 300 volt. So upon using this formula we will get to know that the VRMS is equals to 212.1 volt, and the second question was the RMS value of the current is given and we have to find out peak current. So again using this formula, in this question we have been given the RMS value, so we will have to find out Im. So rearranging this we will get to know that Im, or the peak current, is equals to 14.14 ampere. Thank you. The question says that a 44 millihenry inductor is connected to 220 volt 50 hertz AC supply. Determine the RMS value of the current in the circuit. Now we can pictorially represent this question in this form. Like this is the AC supply of 200 volt and 50 hertz, and the inductor is connected in a series circuit, and the value of inductance is 44 millihenry. Now we have to calculate what is the RMS value of the current in the circuit. Now if we make it equivalent to the DC circuit, then we can see that there we have found out the questions, we have found out the solution of the questions in which this was the resistance and this was the cell. So inductor also possesses some resistance, that is known as inductive reactance XL, and that is defined as omega times L, where L is the inductance and omega is the 2 pi by T, or 2 pi times frequency. Now this inductor will pose this much quantity of resistance, and the inductive reactance is also having the same unit of ohm. Now RMS current would be equal to VRMS by XL, as XL is representing the resistance in the circuit. So we can find out the RMS current using this formula, that is VRMS by XL. We haven't given the VRMS, that is 220 volt, and XL we have to find out, that is inductive reactance. Now inductive reactance can be found out as we have been given the value of L, that is 44 millihenry, and we haven't given the value of omega as well, because omega, as I said, that it is 2 pi times frequency. So 2 pi is 2 into 2 into 3.14 times frequency is given, that is 50 hertz. So the value of XL is going to be 2 pi 50 multiplied by 44 into 10 to the power minus 3, because it is 44 millihenry. Now upon calculating, we will get the value of XL as 13.82 ohm. Now IRMS is equals to VRMS divided by XL. So VRMS is equals to 220 volt, which is given in the question, and XL is 13.82 ohm. So the answer would be 15.92 ampere. Thank you. The question says that a 60 microfarad capacitor is connected to a 110 volt 60 hertz AC supply. Determine the RMS value of the current in the circuit. Now again, this question is similar to the previous question. Again, this capacitor is going to resist some kind of current, and that resistance is given by capacitive reactance, that is XC, and it is defined as 1 by omega C, where omega is 2 pi times frequency. Now again, since this represents the resistance in the circuit, we can give the expression for current as voltage divided by resistance, that is IRMS is equals to VRMS by XC. Now here we have to find out the capacitive reactance, that is XC, and since VRMS is given, we will substitute in the given formula and find out the value of IRMS. Now calculating XC, we will get the value of 44.2 ohm. Now calculating IRMS, that is current, using the formula VRMS by XC, we will get a value of 2.49 ampere. Thank you. The question says that in exercises 7.3 and 7.4, what is the net power absorbed by each circuit over a complete cycle? Explain your answer. Now in both these exercises, we saw that in exercise 7.3 there was an inductor in the series with the source EMF, and in exercise number 7.4 we saw that there was a capacitor in series with the source EMF. Now we have to find out what is the net power absorbed by each circuit over a complete cycle. We have to explain this answer. Now we know that power in AC circuit is given by the formula, that is IRMS multiplied by VRMS multiplied by cos phi, where phi is the phase difference between the source and the circuit. Now for purely reactive circuit, let us assume that the first case of 7.3, that is a inductive circuit, we saw that current lags by the voltage of pi by 2, or the phase difference between the source current and the circuit is pi by 2. Now similarly, we saw that in the capacitive circuits, the current leads the voltage by pi by 2. That is, here the current is leading by pi by 2. Now in both the cases, we saw that there is a phase difference of pi by 2. Now average power, as discussed earlier, is given by VRMS times IRMS times the cos of phase difference. Now cos of pi by 2 is also always going to be equal to 0, since cos pi by 2 is 0. So we can say that power average is equals to 0 in purely reactive circuits. Thank you. The question says that a charged 30 microfarad capacitor is connected to a 27 microhenry inductor. What is the angular frequency of free oscillation of the circuit? Now free oscillations happen when the energy exchange between capacitor and a charged capacitor and an inductor is happening in the circuit. Now this only happens in purely reactive circuit. Now a capacitor and an inductor forms an oscillatory circuit with energy exchange between the electric and magnetic fields. Now angular frequency of the oscillation is determined by this governing equation. So this is basically the implication of Kirchhoff's law. So we know that EMF around the inductor is given by L di by dt. Now dq by dt is equals to L, so it is L di by dt. That is the double differentiation of charge will give us the, with respect to time, will give us the differentiation of current with time, that is L di by dt, plus q by v. This is the potential difference across the capacitor. Now we will come to the conclusion that omega from this governing equation is 1 by LC. That is the angular frequency of natural oscillation in this reactive circuit is going to be 1 by under root LC. Now upon substituting this in the given formula, we will come to know that omega is equals to 1.1 into 10 to the power 4 radians per second. Thank you. The question is saying that a series LCR circuit with resistance of 20 ohm, inductance of 1.5 Henry and capacitance of 35 microfarad is connected to a variable frequency of 200 volt AC supply. When the frequency of the supply equals the natural frequency of the circuit, what is the average power transferred to the circuit in one complete cycle? Now this question can be pictorially represented like this, where this is the power supply, AC power supply of 200 volts, and the frequency is variable over here. Now we have to find out the frequency at which the natural frequency of the circuit meets or the resonance happen. And at resonance, what is the average power transferred to the circuit in one complete cycle? Now we know that resonance in the LRC circuit, that resonance occurs when the inductive reactance equals the capacitive reactance, or mathematically we can represent it as inductive reactance is equals to capacitive reactance. When the inductive reactance and the capacitive reactance matches, the impedance is equals to resistance, or it is purely resistive. So upon equating these two quantities, we will get omega, or the frequency, is equals to 1 by under root LC. Now we can find out the frequency at which the resonance happens by this formula, applying this formula, and after that the power given to the circuit, we have to find out what is the average power transferred to the circuit in one complete cycle. Now when this happens, since the impedance is equals to the resistance of the circuit, so power would be equal to V square by Z, or Z can be equivalent to resistance because there is no other resistance that is happening in the circuit. So R will be equal to, or Z will be equal to 20 ohm. Now upon using this formula for omega, we will find out the value of the resonance frequency about 1380.2 radians per second, and power, we can use this formula of V square by Z, and that will give us, since this is the given quantity 200 volt and Z is equals to the resistance, that is 20 ohm, we will get a value of 2000 watts. So at resonance in this LCR circuit, the average power transfer to the circuit is in one complete cycle is going to be 2000 watts. Thank you. The question says figure 7.17 shows a series LCR circuit connected to a variable frequency 230 volt source, where inductance is 5 Henry, capacitance is 80 microfarad and resistance is 40 ohm. We have to determine the source frequency which drives the circuit in resonance, obtain the impedance of the circuit and the amplitude of the current at the resonant frequency, and determine the RMS potential drop across the three elements in the circuit. Show that the potential drop across the LC combination is 0 at the resonant frequency. Now we know the driving condition for resonance is the frequency of the source matches the frequency of the circuit. So that is the main condition of resonance. And at resonance, the inductive reactance is equals to capacitive reactance, and upon rearrangement for omega, there is the angular frequency, we will get the value of omega is equals to 1 by under root the inductance multiplied by capacitance. And at resonance, the impedance is equals to R, because we know the formula for impedance is under root R square plus capacitive reactance minus inductive reactance whole squared. Now when at resonance XC equals XL, this quantity becomes 0, so Z is equals to R. So at resonance, the impedance is equals to R, or Z equals to R. Now current at resonance is given by voltage divided by the impedance or the resistance, and the peak current similarly is defined by the peak voltage divided by the resistance. And potential drop at resonance is given by VR is equals to Im multiplied by R, where Im is the peak current and R is the resistance. Similarly, VL, that is the potential difference, potential drop across the inductor, is equals to Im multiplied by XL, where XL is the inductive reactance. Similarly, the potential drop across the capacitor is equals to Im multiplied by XC, where XC is the capacitive reactance. So we have to calculate the resonant frequency, we have to calculate the impedance of the circuit, and the amplitude of current at the resonance frequency, that is Im, we have to find out in the second question. We have to find out omega in the first question, and we have to find out potential drop across these three components, that is the resistance and capacitor and the inductor. So omega naught, or the resonance frequency, is given by 1 by under root LC. Upon substitution, we will get to know that it is equals to 50 radians per second. And as discussed earlier, at resonance, impedance is equals to resistance, and that will be equal to 40 ohm, because we have been given that the value of resistor, the resistance of resistor is equals to 40 ohm. So Z will be equal to 40, and the peak current is given by peak voltage divided by R. Now, unless it's specified, the given potential difference is always the RMS. So for calculating the peak voltage, we will multiply it with root 2. So root 2 multiplied by 230 will be the Vm, or the peak voltage, divided by resistance, that is 40, will give us 8.13 ampere. That is Im, the peak current would be 8.13 ampere. So we have solved this question A and B. Now we have to determine the RMS potential drop across the three elements of the circuit. So we have to find out IRMS for that. So IRMS is equals to peak current divided by root 2, and this will give us 5.75 ampere. So potential drop across the resistor would be equal to IRMS multiplied by R. That will give us 230 volt, because R is 40, and 40 multiplied by 5.75 will give us 230 volt. And VL, that is the potential drop across the inductor, is equals to IRMS multiplied by inductive reactance. This will give us 1437.5 volt. Similarly, the potential drop across the capacitor would be given as IRMS multiplied by capacitive reactance. This will give us 1.37.5 volt again. We have calculated XC as 1 by omega times the capacitance, that is 80 microfarad. 80 microfarad, yes. Now we see that VL is equals to VC. Potential drop across the inductor and the capacitor is equals to 0. Thank you. The question is saying that figure 8.5 shows a capacitor made of two circular plates, each of radius 12 cm and separated by 5 cm distance. The capacitor is being charged by an external source not shown in the figure. The charging current is constant and is equal to 0.15 ampere. Now we have to calculate the capacitance and the rate of change of potential difference between the plates. And we also need to obtain the displacement current across the plates. And the third, we have to tell whether Kirchhoff's first rule or the junction rule is valid at each plate of the capacitor. Now we know that capacitance is defined as C equals to epsilon naught A by D, which depends upon the geometry of the plate. Here we have been given that the radius of each plate is 12 cm and they are separated by 5 cm distance. That is, the radius of this plate is 12 cm and they are separated by 5 cm. We also know that rate of change of potential difference is dV by dt. Now V in terms of the capacitance is defined as Q by C, where Q is the quantity of charge. Now if we differentiate V with respect to T, then we will come to the expression of 1 by C dQ by dt, and we can write dQ by dt as I, that is current. So rate of change of potential difference would be equal to I by C. Now let's find out the expression for displacement current. Now we know that displacement current is defined as epsilon naught d phi E by dt, or the rate of change of flux, and flux is defined as E dot A, the dot product of electric field and the area vector. Now E is defined as sigma by epsilon naught, where sigma is the charge density of the plate, so we can write it as Q by A. Now if we find out flux, then A will get cancelled out. Now flux would be Q by epsilon naught. Now displacement current is defined by epsilon naught d phi by dt. After substituting this flux in this expression, we will get epsilon naught multiplied by d q by epsilon naught. So it would be cancelling the epsilon naught, and we will get the value of displacement current equals to I. So the displacement current would be equal to conduction current. Now let's compute capacitance. Capacitance was epsilon naught A by D. After substituting the area and the displacement and the distance between them, we will come to the conclusion that the capacitance is equals to 8 picofarad. Now computing the rate of change of potential difference dV by dt, we already know from here we have calculated that dV by dt would be equal to current by capacitance. Now substituting that in this expression, we will get a value of 1.87 into 10 to the power 10 volt per second. Now computing displacement current, we already saw from this derivation over here that displacement current would be equal to conduction current. So displacement current would be equal to 0.15 ampere. Now it follows the Kirchhoff's junction rule, as at each plate the conduction current flows into the one side while the displacement current flows out of the other side. The question says that a parallel plate capacitor in figure 8.6 made of circular plates, each of radius 6 cm, has a capacitance C is equals to 100 picofarad. The capacitor is connected to a 230 volt AC supply with an angular frequency of 300 radians per second. Now we have to calculate what is the RMS value of the conduction current, and is the conduction current equal to the displacement current. And in third question, we have to determine the amplitude of B at the point 3 cm from the axis between the plates. Now we know that capacitance is a relationship between the charge and the potential difference across the capacitor, and it is given by C equals to Q by V, where Q is the charge and V is the potential difference. And the conduction current for AC voltages, the RMS conduction current is equal to IC equals to omega C by omega C V RMS. Here it comes from V RMS divided by the impedance XC, and we know that XC is for the capacitor is 1 by omega C. So we will get the conduction current as omega C V RMS, and the peak current is related to the RMS current as I peak equals to root 2 I RMS, and magnetic field at a distance r from the axis between the plate is mu naught I peak r by 2 pi r square, where r is the distance of the point from the axis of the plate, and this capital R is the radius of each circular plate. Let's calculate the conduction current. We haven't given the capacitance, that is 100 picofarad, and VRMS is 230 volt, and omega, the angular frequency is 300 radians per second. So RMS current would be equal to IC omega C VRMS. Now substituting in this formula, we will get a value of 6.9 microampere. So the conduction current is going to be equal to 6.9 microampere. Now let's calculate the displacement current. So displacement current arises due to the changing electric field in the capacitor, and Maxwell's equation predict conduction current equals to displacement current. Now since the capacitor is connected to an AC source, the time varying electric field ensures IC equals to ID. So yes, IC is equal to ID here. The conduction current equals the displacement current. Now calculation for the peak magnetic field. Now for calculating the magnetic field amplitude, we will use the peak current. So we will use this formula mu naught I peak r by 2 pi r square. So substituting the values in this formula, we will get a value of 1.63 into 10 to the power minus 11 Tesla. Thank you. The question is saying that what physical quantity is same for X-rays of wavelength 10 to the power minus 10 meter, red light of wavelength 6800 angstrom, and radio waves of wavelength 500 meter. So basically it is saying that what quantity is same for all these electromagnetic radiations, or what quantity is same for electromagnetic radiations. So electromagnetic radiations has same speed, because they all travel with the same speed of approximately 3 into 10 to the power 8 meter per second. Now this constancy arises from the Maxwell equation, which predicts the electromagnetic waves are self-sustaining oscillations of electric and magnetic fields. We also know that C, or the speed of electromagnetic wave, is equals to frequency times lambda. So this speed is going to be same. What changes is wavelength or the frequency. Thank you. The question says that a plane electromagnetic wave travels in vacuum along z direction. What can you say about the direction of electric fields and magnetic field vectors? Is the frequency of wave, if the frequency of wave is 30 megahertz, what is its wavelength? Now we know that electromagnetic waves consist of oscillating electric and magnetic fields that are perpendicular to each other and the direction of the wave propagation. These fields are described by Maxwell's equation, which predict that E and B are perpendicular to each other. Both E and B are perpendicular to the propagation vector k, that is the direction in which wave is propagating, that is in the z direction. So both E and B vector is going to be perpendicular to the z axis or the k cap direction. Now for a wave propagating in z direction, E would be perpendicular to the z and B is also going to be perpendicular to z, and E and B are mutually going to be perpendicular. So you can assume that E is along the x-axis and B is along the y-axis. Now we have to find out the wavelength of the wave whose frequency is going to be 30 megahertz. So the frequency of the wave is given as 30 megahertz or 30 into 10 to the power 6 hertz. The formula for calculating wavelength is the speed divided by frequency. So speed is going to be 3 into 10 to the power 8 meter per second, which is going to be constant, and frequency is 30 megahertz. So after dividing it, we will get a value of 10 meter, that is wavelength is 10 meter. Thank you. The question is saying that a radio can tune into any station in 7.5 megahertz to 12 megahertz band. What is the corresponding wavelength band? So we know that the wavelength can be defined by the speed divided by frequency, and we have to find out here that given the range of frequency, what is the range of wavelength? Wavelength band means the range of wavelength. So here lambda can be calculated by dividing the speed with frequency. So let's calculate. The highest frequency is 12 megahertz and the lowest frequency is 7.5 megahertz. So corresponding with the lowest frequency, there will be the higher wavelength, that is for frequency maximum 12 megahertz. The wavelength is going to be 25 meter, and for the lower frequency, lambda is going to be maximum, that is 40 meter, because lambda equals to c by nu and nu equals to c by lambda. So they both are inversely proportional. So if frequency is maximum, lambda is going to be minimum, and if frequency is minimum, then lambda is going to be maximum. So we come to the conclusion that the wavelength band is going to be 25 meter to 40 meter. Thank you. The question says that a charged particle oscillates about its mean equilibrium position with a frequency of 10 to the power 9 hertz. What is the frequency of electromagnetic waves produced by the oscillator? So we know that accelerated charges radiate electromagnetic waves, and the frequency of the electromagnetic waves equals the frequency of the oscillation of the charge. So we can say that the frequency of the wave produced is identical to the frequency of the oscillating charge, and it is going to be same, that is 10 to the power 9 hertz. So the frequency produced, the frequency of the electromagnetic wave produced is going to be of the magnitude 10 to the power 9 hertz. Thank you. The question says that amplitude of magnetic field part of the harmonic electromagnetic wave in vacuum is B naught equals to 510 nanotesla. What is the amplitude of electric field part of the wave? So we know that electric field and magnetic field are related, as electromagnetic wave consists of oscillating electric and magnetic fields. These fields are perpendicular to each other, and the direction, and they are also perpendicular to the direction of the wave propagation. And the amplitude of the field is given by, they are related by E naught equals to CB naught, that is electric field magnitude is equals to the speed of electromagnetic wave times the magnitude of magnetic field. Now here speed of the electromagnetic wave is 3 into 10 to the power 8 meter per second. Now we have been given the value of B naught, that is the magnitude of magnetic field. We have to find out the value of E naught. So in this formula, only E naught is the unknown. We know the value of C and we know the value of B naught as it is given in the question. So substituting in this formula, we will get a value of E naught, that is the magnitude of electric field, as 153 Newton per Coulomb. Thank you. The question says that suppose that the electric field amplitude of an electromagnetic wave is E naught equals to 120 Newton per Coulomb and its frequency is 50 megahertz. we have to determine the magnitude of magnetic field, omega, angular frequency, k wave number, and the lambda, that is the wavelength. So we know that B naught equals to E naught by C, or the magnetic field magnitude is equals to the electric field magnitude divided by the speed of electromagnetic wave. So upon using this formula, we will get the value of B naught, that is 4 into 10 to the power minus 7 Tesla. For angular frequency, we know that angular frequency is 2 pi by T, or 2 pi nu, or 2 pi into frequency. We have been given the value of nu, so we can easily calculate angular frequency omega over here, that is 3.14 into 10 to the power 8 radians per second. For wavelength, we know that the formula is the speed of electromagnetic wave divided by the frequency. After substituting the values, we will get the value of 6 meters. So this is the wavelength. For wave number, we know that it is 2 pi by lambda, or the wavelength. So after substituting the values, we will get a value of 1.05 radians per meter. So this is the wave number. Having calculated all these values, we have to now find out the expression for E and B, that is electric field and magnetic field. So we assume that electromagnetic wave is moving in the x direction. So electric field will be along y direction, and the magnetic field will be along z direction. So this is the general expression for the electric field and the magnetic field. Now substituting the values of E naught, that is the peak magnitude of electric field, and k, that is the wave number, and omega, that is the angular frequency, we will get the expression for electric field of this electromagnetic wave. Similarly, substituting the values of corresponding values of the magnetic field, that is the magnetic field magnitude, wave number, and all, we will get the value of the expression for magnetic field in this electromagnetic wave. Thank you. The question says that the terminology of different part of electromagnetic spectrum is given in the text. Use the formula E equals to h nu for energy of quantum radiations, photons, and obtain the photon energy in units of electron volt for different part of electromagnetic spectrum. In what way are the different scales of photon energies that you obtain related to the source of electromagnetic radiations? We have to find out photon energy, or the energy of these electromagnetic radiations, and the band is this. For radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, we have to find out their energy in electron volts, and also we have to find that we have to give a way, we have to tell in what way are the different scale of photon energies that you obtain related to the sources of electromagnetic radiations. So let's start. We know that energy of a photon is given by E equals to h nu, where h is the Planck's constant with the value of 6.63 into 10 to the power minus 34 joules second, and nu is the frequency of the radiation. Now if we relate joule with electron volt, then 1 joule would be equal to 6.242 into 10 to the power 18 electron volt. Now frequency and wavelength are related using this formula, that is C equals to nu times lambda, or we can say that frequency is equals to C by lambda, where C is the speed of the electromagnetic wave and lambda is the wavelength. Now this is the table which represents the electromagnetic spectrum with their wavelength and the energy level. So we can see that as the wavelength is reducing, frequency is increasing and energy is also increasing. We can see that the least energy is of that of the radio waves, which is having a much higher wavelength, much higher than 0.1 meter, and they have frequency of less than 3 into 10 to the power 9 hertz, and they have energy less than 10 to the power minus 5 electron volt. And the gamma rays is having the least wavelength, that is of order of less than 10 to the power minus 11 meter. They are having higher frequencies, 3 into 10 to the power 19, and the energy, they are having the highest energies of 1.24 into 10 to the power 3 electron volt. Now we in this pattern we see that the photon energy increases with frequency and decreases with wavelength, and also we see that higher frequency electromagnetic waves are more penetrative and interact strongly with the matter. Now these diversity in photon energies allows electromagnetic waves to be utilized in various applications. Thank you. The question says that in a plane electromagnetic wave, electric field oscillates sinusoidally at a frequency of 2 into 10 to the power 10 hertz and the amplitude of 48 volt per meter. Now what is the wavelength of the wave? what is the wavelength of the wave and what is the amplitude of oscillating magnetic field, show that the average energy density of E, that is electric field, equals the average energy density of magnetic field. We have been given the speed of electromagnetic wave as 3 × 10⁸ meter per second. Now we know that electromagnetic waves consist of oscillating electric and magnetic fields which are perpendicular to each other, and they are also perpendicular to the direction of the wave propagation. Here we have to find out the wavelength of the wave and the amplitude of the oscillating magnetic field, and that is B naught. We have to find here B naught, and we have to find out lambda over here. And we also need to show that the average energy density of E, electric field, equals the average energy density of magnetic field. So the formula for calculating wavelength is speed of the wave divided by frequency, but before that we should clear some of the facts. The speed of electromagnetic wave in vacuum is 3 × 10⁸ meter per second, and the relationship between electric field and magnetic field is given by B naught, that is the magnetic field is equals to electric field divided by the speed of this electromagnetic wave. Now energy density of electric field and magnetic field is given by the electric field energy density is epsilon naught, the magnitude of electric field squared divided by 2. Similarly for magnetic field, the energy density is given by the magnitude of magnetic field squared divided by 2 mu naught, where mu naught multiplied with epsilon naught is equals to 1 by c square. So let's calculate the wavelength. The frequency of the wave was 2 × 10⁻10 Hertz, and the speed of the light was c equals to 3 × 10⁸ meter per second. So for formula for calculating wavelength is c by frequency, that is the speed of the wave by frequency. Now lambda, upon substituting the values over here, we will get a value of 1.5 × 10⁻⁻2 meter. So the wavelength is going to be equal to 1.5 centimeter. Now let's find the magnitude of magnetic field. So we will use the formula, this formula over here, B naught equals to E naught by C. Electric field amplitude is given as 48 volt per meter, and the speed of light is given as 3 × 10⁸ meter per second. So upon substituting the values over here of E naught and C, we will get a value of B naught, that is the magnitude of magnetic field, as 1.6 × 10⁻⁷ Tesla. Now we have to show that the energy density of electric field and magnetic field are same. So we will see the expression for electric field density, that is epsilon naught E square by 2. Similarly for magnetic field it is this. Now using epsilon naught into mu naught equals to 1 by c square, and this the relationship between electric field and magnetic field magnitude, we will come to a conclusion that EB is equals to UE, or the energy density of electric field is equals to energy density of magnetic field. Thank you.